Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. The math associated with electronics can be pretty intimidating. When I was in engineering school, it did indeed get pretty heavy. And for that reason, most people tenaciously avoid it. But it doesn't have to be this way if you take your time, because most of what we need to do can be accomplished with algebra. Now, the algebra can look very complicated and hard, but it's not as hard as it looks. And this is exactly what I'm going to be covering in this video. I'm going to walk through a very simple example doing the pencil and paper math to come up with an equation for the frequency response of a simple circuit. I will also show you how to let Excel do all of the calculations for you. You will find a link to a zip file in the description below, which contains a PDF walkthrough document and the spreadsheet I generated making this video. The next video in this series shows you how to avoid all of this heavy lifting. But where's the fun in that? If you have any questions or comments, please feel free to add a comment to this video. I do make a concerted effort to respond to every single comment. If you find this video helpful, please click on the like and subscribe. Don't forget to subscribe to the channel. So let's begin our video by wading into the preliminaries. Before we begin, I want to give some friendly advice as one who has struggled through this math. It is tedious, and you need to be meticulous in order to gain success. And I want you to be successful. That is the whole point of this video. Now, one of the first mistakes people make when approaching this is making the assumptions at the outset that it is impossible. If we are convinced that it cannot be done before we even try, this poisons our ability to do it. I want to encourage you just to take your time, take it as slow as you need to take it. There's no rush. Set it aside. Come back to it again if you must. The second mistake is when we try to skip steps by doing stuff in our head without first writing it down. It is absolutely amazing how totally cattywampus we can get ourselves by not writing down each step. And I've done this. I've gotten impatient with the process, thinking I can jump ahead, not writing down everything I'm doing before I try to do it, and, well, failure. So if you're going to multiply by something, write out what you're going to do, then do it. Believe me, it really helps to be able to actually see it on paper, what you're doing. The last important piece of advice is to be painfully careful with the signs. It is so very, very, very easy to get a sign wrong on something somewhere and then have it all come out totally wrong because of it. I've done this way too many times. Make a conscious, concerted effort to properly carry through the signs and double check yourself. Now, I've chosen a simple circuit which consists of a single resistor and a single capacitor. And I'm going to walk through this whole process step by step by step. And I've provided a complete document with all of this in it for you. Look for a link to a zip file in the description. This zip file will contain two things. First, it has a PDF document with this step-by-step process. And this is a great thing to have in hand as you follow along with me in this video. If I were you, I'd pause the video right now, download the zip file, print out this document so that you can follow along with me. The second thing in there is the Excel spreadsheet that I generated by following these steps. Okay. Now I'll wait a little bit for you to go and get that zip file. Doo-doo. Before we dive into the math, I thought it would be a good thing to cover two important things you will be seeing in here before we actually see them. And circuits which contain reactive elements like capacitors and inductors, the expressed impedances and voltages and voltage gains and so on are all in what we refer to as complex numbers. That is, they contain the impossible number represented by the symbol J. For more information on this impossible number, see my video on the 3 impossible numbers. I've put a link for this up in the corner here just for you. A complex number is in the form R plus Ij, where R is the real portion or the resistive portion from an electronics perspective, and the I is the imaginary or reactive portion from an electronics perspective, and is generally represented by the letter X. So it becomes R plus Xj, R plus X times J. Now, J is the impossible number, the square root of -1. So J times J is the same thing as J squared, which equals -1 because the square root of -1 is J, and so on and so forth. Secondly, there are going to be times when we will be multiplying two of these complex numbers together like this. We have R1 plus X1 times J multiplied by R2 plus X2 times J. Well, how do we do that? Well, this is where we need to be really careful not to allow the math to intimidate us. It's not hard, it's just, well, tedious. First, we multiply the second entity through by R1. So it's R1 times R2, and then R1 times X2 times J, so plus, because there's a plus here, so R1 times X2 times J. So that's the first part of this, dealing with just this. Then we multiply the second entity through by our X1 times J. So we get X1 times J times R2 plus X1 times J times X2 times J. So it ends up coming out to be this whole mess here with a plus sign in between these two. So this multiplication equals this big mess here. Well, we need to simplify this. We have real terms like this guy right here, that's a real term, and we have reactive terms like this one because it's got a J in it. This one's got a J in it. So, but we can do something about this one here. This is where we're going to focus our attention first. We have X1 times X2 times J times J. Well, J times J is -1. Oh, so that means that we have X1 times X2 times a -1, which gives us minus X1 times X2 for this last term. Next, we want to gather together our imaginary terms, and we see here we have a J term here, we have a J term here, R1 times X2 times J, we have R2 times X1 times J. We put all those together and combine them into a single term, so we end up with R1 times X2 plus R2 times X1 all times J. So this right here is our imaginary or reactive term. And notice here we have a real term here because there's no J in it. And what happened to this one down here? We have a real term because there's no J in it. So the real term of this whole equation is R1 times R2 minus x1 minus or times x2. And there's our real term. So let's put that all together into one big happy equation. And so we end up with this big happy equation here. So R1 plus x1 times j times R2 plus x2 times j, multiplying these two together, gives us this real portion here, the resistive portion of R1 times R2 plus x1 times x2, and the imaginary or reactive portion of R1 times x2 plus R2 times x1, all multiplied by our lovely impossible number j. Now we are ready to start working on our circuit. Now that we're ready to dive into the math, well, hang on. Let me introduce you to our circuit. We have the input voltage, Vn, and this is connected to the series combination of a 10 k ohm resistor and a 1 nanofarad capacitor, otherwise known as a 0.001 microfarad capacitor. The output is taken from across the capacitor. Because of the frequency-dependent nature of the impedance of this capacitor, this forms a frequency-dependent voltage divider. In this case, it is a rudimentary low-pass filter. The standard equation for a voltage divider, Vout, is equal to Vin times Zout divided by the sum of Zin and Zout. Now with our voltage divider, Zin is the resistor Rn. The impedance of this resistor Rn is just the value of this component. Zout, or the impedance output, is found in the capacitor C. The impedance of the capacitor is a frequency-dependent reactive entity. The equation for the impedance of the capacitor is minus J divided by 2 times pi times the frequency in hertz times the capacitance in farads. Well, in the electronics world, frequency is actually expressed in radians/second. And there are 2 times pi radians for each trip around the circle or each cycle of a sine signal. So when we see the equation 2 times pi times f in it, they are changing the frequency from cycles per second or hertz into the frequency in radians/second, and then representing this with the lowercase Greek letter omega. The equation for the impedance of the capacitor becomes minus J divided by omega times the capacitance in farads. Now we get to put everything into our voltage divider equation, and it looks a little bit intimidating. We have Vn times minus J over omega times C, all divided by Rn plus minus J over omega times C. Well, the first problem is that we have a mixed number in the bottom that we'd like to clean up. Now, we remember that anything divided by itself is equal to 1. If we create a fraction with the same thing on the top as we have on the bottom, it is equal to 1. So we create a fraction of omega times C divided by omega times C, and then multiply the Rn on the bottom by this so we can get a common denominator. And so that gives us this big equation here. See the Vn times minus J over omega times C on the top. But look at the bottom. We have Rn times the omega times C divided by the omega times C plus minus J over omega times C. Now we multiply this out. And so we end up with that blob on the top divided by the omega times Rn times C divided by omega times C on the bottom plus minus J over omega times C, all that on the bottom. Now notice that omega times C is under both the omega Rn times C and the minus j terms on the bottom, which means that we can combine the numerators and we end up with the blob on the top, all divided by omega times Rn times C minus j divided by omega times C. Now, notice that we have a fraction on the top and a fraction on the bottom. Both have the same denominator. This means that we can simply get rid of the denominators. So we end up with minus Vn times j on the top. And then on the bottom, we have omega times Rn times C, all minus j. But we have another problem in our denominator. Notice that we have a complex number in the denominator. Well, we don't want to have a complex term in the bottom. We only want a single complex term that is in the numerator. So we perform some fancy math trick. We can turn the complex number on the bottom into a real number. To do this, we multiply the entire equation by a fraction which has its complex conjugate on the top and on the bottom. We know this is equal to 1 because anything divided by itself is 1, so it doesn't change the value of the overall equation. What is a complex conjugate? A complex conjugate is nothing more than the same complex expression with the sign of the imaginary portion swapped. Thus, our omega times Rn times C minus j becomes omega times Rn times C plus j. We have the complex conjugate. Notice that the only difference between the two is the sign of the j term. Well, how does this help us? Well, it leverages the following algebraic truth. A minus b times a plus b is equal to a times a minus b times b, or a squared minus b squared. So in our case, a is equal to omega times Rn times C, and b is equal to minus j. So for the denominator, the guy on the bottom, we get omega times Rn times C minus j is multiplied by omega times Rn times C plus j, and this gives us omega times Rn times C squared minus the negative j squared. Now, any negative number multiplied by itself is a positive number. So minus j squared is the same as j squared. And we know that j is the square root of minus 1. So j squared is minus 1. So if we go back to our equation, we see that we have omega times Rn times C, that quantity squared, minus a minus 1. If we subtract a negative number, it is the same as adding a positive number. So we are left with omega times Rn times C, that quantity squared, plus 1 on the bottom of our equation. Now let's turn our attention to the numerator. I'm ultimately looking for the voltage gain of this circuit, and voltage gain is the output voltage divided by the input voltage, or V out over Vin. Now I have Vin in the numerator, so the first thing I'm going to do is divide both sides by Vn. Now this does two things for me. It gets Vn out of the numerator on the right side of the equation, and it gives me an expression for the voltage gain on the left side of the equation. So we end up with V out over Vn is equal to minus j times this complex conjugate, which is the omega times Rn times C plus j, all divided by our newfound denominator omega times Rn times C squared plus 1. Now we get to multiply through the numerator. In the numerator we have a minus j times omega times Rn times C plus the minus j times j. Now remembering j times j is minus 1, but we have minus j times j. We can pull that negative sign outside the parentheses. We get a minus sign, left parenthesis, j times j, right parenthesis, which becomes a minus 1, and a minus 1 is a plus 1. So our minus j times j term becomes very simply plus 1. So we end up with V out over V in is equal to minus j times our omega times Rn times C plus 1 on the top, and then our newfound denominator on the bottom. Now looking at the numerator, we can see that the j term is on the left side of the equation, and the standard way of writing this is with the j term on the right in the form r plus xj. So I'll rearrange things so it looks like this. We end up with V out over Vn is equal to, here's the numerator, the top side, 1 minus the quantity omega times Rn times C times j, that's the top. The bottom is all real. It's omega times Rn times C, that quantity all squared, plus 1. Now, we can pat ourselves on the back. We did it. We got to it. But we have a problem. We can't sit down with our calculator and calculate any values with this. Why is that? Because this is a complex entity which resides in the complex plane. It exists as a vector quantity on this plane. To make this into something we can easily calculate, we have to determine the magnitude and the direction or phase of this vector. Let's talk about the whole complex plane thing just for a little bit so we get our head screwed on straight here. A vector has both magnitude and direction. The length of the vector is its magnitude. The endpoint of this vector is defined by its coordinates on the xy plane. That vector forms the hypotenuse of a right triangle. The length of this hypotenuse is found by the length is equal to the square root of the x-coordinate squared plus the y-coordinate squared. Well, the x-axis corresponds to the real portion of our complex entity. The y-axis corresponds to the reactive or imaginary portions of the complex entity. So we have our equation, 1 minus this omega Rn C times j on the top, and then we have the real on the bottom. And if we break this up into real and imaginary portions, the real part is simply the 1 divided by the denominator, which is a real number. And the imaginary part is that minus omega. Notice that we're carrying that sign down with us. It's minus omega times Rn times C divided by that real quantity that's on the bottom, omega Rn C squared plus 1. Now, if we take these two things and square each of them, and then add these two squares together, and then finally take the square root of this sum, then we get the magnitude of this vector. So the magnitude of this vector can be found by this big, nasty looking equation. Wow, look at this. This big square root sign and all this stuff inside. But notice inside, both of the terms inside of this have the same denominator. So we can simplify this a little bit. We can, 1 squared is, well, 1, And so we have the 1 plus, and then we have omega Rn C all squared on the top. And then we have the common denominator on the bottom all squared. This is a lot simpler. Now we have something that we can sit down with our calculator and calculate the voltage gain of this circuit with the given values of Rn and C for any given frequency. Now, let's turn our attention to the direction or phase of this vector. The direction or phase of the vector is determined by the angle between the horizontal or real axis and the vector. This angle may be found by using the inverse tangent, or as some call it the arctangent, using the xy coordinates of the end of the vector. The equation for this is the phase, or the phase angle, is equal to the inverse or arctangent of y divided by x. Now, as before, the x corresponds to the real portion, and the y corresponds to the imaginary portion. Now, we remind ourselves of the real and imaginary portions of our v out divided by v in equation. You see them both here on the screen, these two lovely looking things. Now, if we take these things and we stuff them into our arctangent equation, we get this rather intimidating looking thing. But notice that the fractions on the top and on the bottom both have the same denominator again. Look at that. They both have omega times Rn times C squared plus 1, top and bottom, which means we can do what? We can eliminate them. And so if we get rid of the denominators and the fractions on the top and bottom, what are we left with for a denominator in this fraction? Simply a 1. So the final simplified equation for the phase response of our circuit turns out to be this very simple equation. The phase angle is equal to the inverse tangent or arctangent of minus omega times Rn times the capacitance. Wow, I bet you didn't expect it to come out so nice and tidy. So now we have all of the equations that we need, so we can sit down with our calculator and calculate values to determine the frequency and phase response of our simple low-pass filter. We have the magnitude, which is this big square root equation with all this stuff in it, or if we want to express it in dB, we take that and we multiply the logarithm to the base 10 of that quantity times 20, and we get quantity in decibels, or dB. We use the 20 times the log version of the dB formula because we're talking about voltage gain here as opposed to power gain. And then we have our phase equation, which we just learned, which is the inverse tangent of the minus omega times Rn times C. But who wants to sit down with a calculator and do this one frequency at a time? Not me. So we're going to let Excel do the calculations for us. To make this make sense and be easy, we must be organized and thoughtful in how we set up our spreadsheet. The first step in letting Excel do the calculations is to create cells for the component values and then naming these cells so that they slide neatly into our equations. As you can see here, I chose cell C2 for the value of the resistor Rn in ohms, and D2 for the capacitor value in farads. I labeled these in C1 for Rn and D1 labeling that as C. So I knew exactly what these values were down here. And then I went in and named these values. To name a cell value, you right-click on the cell, you go down to Define Name, and then you type in the name. Now I've already defined this as Rn. Same thing here, I defined this one as C underscore. Now, we need a column which will hold the frequency in hertz. So I chose to start my column of numbers at A6 to allow me room for headings and stuff, so I knew exactly what was what up here. And then we fill this column, starting at A6 and going on down, with values filled whatever way you like for your particular design. With this particular design, I chose to start at 1 hertz, going at 1 hertz steps until I got to 100 hertz. Then from 100 hertz to 10 kilohertz, I used 100 hertz steps. And then from 10 kilohertz to 100 kilohertz, I used 1 kilohertz steps. And then finally, from 100 kilohertz to 1 megahertz, I used 100 kilohertz steps. And so I have quite a few values here, as you can see, which is kind of good. It kind of fills in the gaps. Now, as before, we're going to select all of these values in the column, and we're going to right-click, and we're going to do define name, and we're going to define that entire column of values as F underscore for frequency. Now, our equations use omega, which is equal to 2 times pi times the frequency in hertz. I have a column of frequency in hertz, so I would like to have a column that has the values of 2 times pi times the frequency in hertz, or omega. So I'm going to create that starting at B6 and enter the equation equals 2 asterisk pi left parenthesis right parenthesis asterisk F underscore. And then copy this cell down the entire column for all of the values in the frequency column. Like before, we're going to select all of the values in the B column. We're going to right-click on those selected values. We're going to choose Define Name from the pop-up menu, and then we're going to name this column of values W underscore. If we look at the equation, we can see that there is a common expression in both the numerator and the denominator. It is omega times Rn times C, that whole quantity, squared. So if there's a common expression like this, it's really nice to create a column just for that. And so here we have, starting at C6, that exact thing. In cell C6, I entered equals, left parenthesis, W underscore times Rn times C underscore right parenthesis, caret 2, which is the same thing as omega times Rn times C all squared. And now we copy that down the entire column for every value of frequency. Now we're finally ready to calculate the magnitude of the voltage gain. We will do this in column D. In cell D6, type the following formula. Equals SQRT, left parenthesis, 1 plus C6. Remember, C6 is our common entity here. All divided by this big quantity, C6 plus 1 squared. Now, if you carefully compare this to our V out over V in magnitude equation, you can see that this is exactly what we just entered. Now copy this down the entire column for every frequency. Now we have the voltage gain for every frequency defined in our A and B columns. Well, what about the whole phase thing? Now we'll calculate the phase starting in column E. And we do that by entering the following formula in E6. Degrees, left parenthesis, arctangent or atan, left parenthesis minus W underscore star Rn star C underscore right parenthesis. Now, Excel thinks about angles in terms of radians. We think of them in terms of degrees. So in this equation, we're using Excel's degrees function to convert the angle reported by Excel into radians into our familiar degrees. Now, copy this down the entire column as before. Now, but we want the voltage gain to be expressed in dB. So that's really easy. It's just 20 times the log 10, which means Excel is doing a logarithm to the base 10 of the value of the voltage gain in cell D6. Now we use the 20 times the log formula because this is calculating dB from voltage gain as opposed to power. Now copy that down the entire column. And so now you have the voltage gain expressed in dB for every frequency in columns A and B. Well, you might want to see this on a graph. So you can create your scatter graph using frequency as the x-axis, and whichever entity, voltage gain expressed in dB or phase, and you could put those on the y-axis. When you do, be sure to change the x-axis to show the values in logarithmic sequence. So let's choose a graph that I made here. So to change the x-axis to indicate in logarithmic scale, you select the x-axis, you right-click on it, you go to Format Axis. Over in the far right-hand side, it says Format Axis. You have these little icons. You want this one over here, Axis Options. Down here a ways, you see Logarithmic Scale. And you just make sure that this checkbox is checked. Without it checked, your graph is going to look something like this. With it checked, it looks something like this. Well, that wasn't so bad now, was it? In the next video, I will show you how to avoid all of this heavy lifting. Let's let Excel do it for us. Easy peasy. If you found this video helpful, please click on the like and don't forget to subscribe to the channel. Thank you so much for watching. Until next time, Toodle-oots.